A battery that could theoretically provide power for several thousand years, but it's nothing like what you might expect. Researchers from the University of Bristol and the UK's Nuclear Regulatory Authority unveiled the first carbon-14 diamond battery in the late 2024. What makes it special, it uses an isotope with a half-life of over 5,700 years and is designed for devices that need a power supply for a very long period of time. In this video, we will look at how it works, what its limitations are, and where it's currently being installed. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's! Diamond batteries belong to the group of radionuclide or nuclear batteries, and they are not new, but a lot has happened in the last years, and it's time for an update. The idea behind such batteries is actually very old. Generating electricity from radioactive decay has been discussed since the 1960s and has been used, for example, in space travel. Transit 4A was the first nuclear-powered satellite navigation system in 1961. Nuclear-powered pacemakers were also implemented in the medical field in the 1970s. It's important to note that these batteries work fundamentally differently from the rechargeable batteries we are familiar with in everyday life. They don't store energy chemically, but instead explicitly use radioactive decay itself as an energy source. But what actually can we expect from this new diamond battery? Before we can understand how such a diamond battery works, we first need to take a look at what the energy source carbon-14 actually is. Carbon-14 is a special variant of the chemical element carbon in the periodic table. Carbon is abbreviated with a C, which comes from the Latin word carbo and simply means coal. The 14 tells us how many particles are packed into the atomic nucleus. Carbon, for example, always has 6 protons, but the number of neutrons can vary in atoms. These are then called isotopes. For C14, that would be 6 protons and 8 neutrons. The isotope C12, which is actually present in large quantities in our bodies, has 6 protons and 6 neutrons. C14 is radioactive due to the number of neutrons, which ultimately means that an atomic nucleus is not permanently stable. It eventually changes on its own and emits radiation in the process. Many of you have probably heard of C14 in connection with the radiocarbon dating method. This method can be used, for example, to determine the age of bones, wood, or archaeological finds simply by observing this decay. With our battery, however, the key point is that energy is released during the decay of C14. This radioactive decay in carbon-14 is also known as beta-minus decay. Due to the instability of the atom, a neutron in the nucleus transforms into a proton. In the process, an electron and an antineutrino are released. Through this decay, C14 then forms into nitrogen-14 atom. In the periodic table, nitrogen has the symbol or letter N, which comes from Greek and Latin. The mass number remains the same, but the atomic number increases from 6 to 7 because a neutron becomes a proton. The antineutrino is an electrically neutral elementary particle that, due to its very low mass, hardly interacts and can be neglected from the battery. So it is therefore sufficient to know C14 decays into nitrogen-14, releasing an electron in the process. The emission of such a particle can be made visible using a cloud chamber. This is a device in which charged particles leave fine tracks in a supersaturated vapor as they pass through. Put simply, it's a device that makes radioactive radiation directly visible to us. I think it's a very cool thing. I think we had one in school and later in university, and I don't know, it blows my mind. When a C14 sample is placed in such a cloud chamber, small tracks can therefore be seen forming continuously. The decay of an entire block of C14 occurs continuously, and this is precisely where an important concept comes into place: the half-life. The half-life indicates how long it takes for only half of a given amount of radioactive element to remain on average. For C14, the half-life is 5,730 years. That means if I have 1 kilogram of C14 today, in 5,730 years I have only 0.5 kilogram left, and after 11,460 years only 0.25 kilograms. And that makes C14 so interesting for building a battery. That's why you sometimes read that such a battery could theoretically function for millennia and even outlast an entire civilization. But now comes a really exciting question. How does this radioactive decay actually generate electricity? Tom Scott, a professor at the University of Bristol, not the super cool YouTuber I'm a big fan of, compares the principle to a solar cell. In there, photons, or particles of light, strike a material and dislodge electrons. These free electrons then flow through a circuit, and moving electrons are simply electricity that can be used. In the diamond battery, however, the energy does not come from light, but from the radioactive radiation itself. The electrons produced by beta-minus decay are high energy. This means they carry a great deal of kinetic energy. When these electrons penetrate the semiconductor material, they transfer energy to the atoms through collisions, thereby generating additional electrons. To guide these free-moving electrons in a specific direction, the battery is designed so that an electric field directs the electrons, thereby generating a current that can be used. But now, of course, you might ask, why do I need a diamond for this? Chemically speaking, a diamond is essentially just carbon, but in a very specific crystal structure in which the carbon atoms are extremely tightly bonded to one another. This makes it not only one of the hardest known materials, but also gives it properties that are technically advantageous for such a battery. For one thing, diamond is highly resistant to radiation. For another, synthetic diamonds can effectively be used as a semiconductor. Furthermore, diamond dissipates heat very effectively, which is also an advantage for technical components. Manufacturing such a diamond battery is not that simple at first. The idea is to take graphite from old reactors that contain C14. This radioactive carbon is extracted from the material under controlled conditions through intense heating, so that the carbon can be released as a gas. This C14 containing gas is then pressed into an artificial diamond under low pressure and high temperature. This diamond is radioactive and emits the beta-minus radiation we just mentioned. To harness and shield the radiation, this layer is encased in non-radioactive C12 diamonds. This also serves as a semiconductor. An internal electric field, for example, created by a p-n junction, ultimately dissipates the resulting electrons. However, the exact details regarding the implementation of the electric field have not been officially disclosed. Actually, I then asked myself what actually happens to the nitrogen produced by the beta-minus decay, because we remember it is produced. Does it damage the battery, or does the material wear away over time? In fact, N14 continues to accumulate in the battery, but that doesn't mean the diamond immediately becomes unstable. Its crystal lattice can actually accommodate nitrogen atoms to a certain extent, where they take the place of carbon atoms. There's, however, a limit to this so-called substitution nitrogen. That is a range within which the material can still tolerate the incorporated nitrogen atoms without undergoing significant changes. And that is precisely why this is not an urgent problem in practice. Due to the long half-life of C14, it would take many hundreds of years before this transformation would have any noticeable effect on the battery. Another very exciting aspect is the question of where the researchers plan to source the radioactive C14, and the beauty of this is that radioactive waste can be recycled here. Approximately 97,000 tons of this material are stored in the United Kingdom alone. Extracting C14 from it would yield two positive effects. Use part of the radioactive waste as a raw material while simultaneously reducing the radioactivity of the remaining graphite. But it's not that simple, because dealing with radioactive waste remains one of the greatest technical and societal challenges of all times. In this context, I'd like to mention the topic of partitioning and transmutation. Though that's a subject for another video I made recently, I visited a startup that's currently planning to convert a nuclear power plant in Germany for transmutation. And we went to the old power plant to see how it's supposed to work, and many of you haven't seen the video yet. I will link it in the end of this video. It's a great video, please watch it. So the key point here, and this is also the crucial difference from earlier concepts that were involving nickel-63 for batteries, is that with nickel-63, radioactive material had to be specifically produced artificially in reactors, which generally leads to additional nuclear waste. The major advantage of the new battery, therefore, is that we reuse existing raw material from the nuclear cycle. Let's assume that such a diamond battery would be used and compared to something we're familiar with from everyday life, a standard AA battery. I think it's AA outside of Germany too. If not, please let me know in the comments. So a conventional AA battery stores roughly 0.002 to about 0.005 kilowatt hours of energy. It can release this energy in a relatively short time. This is precisely why it is particularly suitable for devices that require a comparatively high amount of power immediately at the push of a button. With a diamond battery, it's completely different. If we take 1 gram of C14, we simply have 750,000 kilowatt hours of energy in there. Compared to our AA battery, that's just 375 million times more. But that energy is only released over 5,730 years, which works out to just 0.0000417 kilowatt hours per day. This puts it in a microwatt range in terms of power, but with a very high energy density. You just can't access the energy quickly. In other words, a single AA battery contains roughly as much energy as a diamond battery would only release after 480 days. And that's actually the first major hurdle, so to speak. So one has to put this into perspective, because this type of battery simply has a different use case. And that is why the question is important: what is it supposed to power? The University of Bristol says this technology is not a replacement for AA batteries. The applications for this technology focus on devices with long lifespans and low power consumption, such as small electronic devices for space exploration, medical devices, undersea communication systems, etc. Essentially, the technology is designed for applications where low power consumption is required to keep devices operational or preserve stored data, and where battery replacement is not possible or inherently costly. Okay, but we still have to look at some other big hurdles. You know, it's in every of my videos, the part where we look at the limitations and hurdles of new innovations, and every new innovation has some hurdles. A really big hurdle for me is actually the framing that this technology helps with nuclear waste recycling. On this topic, I found a statement by George Steinhauser from TU Wien, who says that even if all the C14 in the world were used in this way, the reduction in the burden on a nuclear waste repository would not be noticeable. And the problem is also that the enrichment or processing of such isotopes can initially be very energy intensive. Furthermore, even if the radiation is well shielded during normal operation of the diamond battery, radioactive material remains inside. Steinhauser points out that especially with broader use, the risk of this material being released in the event of damage must also be considered. For example, through combustion, since diamond burns at just 850 degrees. In conclusion, and this is a view shared by most of the research I found, the battery has great potential in specialized applications, for example in space exploration, deep sea missions, the military sector, or industrial facilities. In other words, where devices are needed to operate as reliable as possible over a very long period, and where replacing the battery would be difficult, expensive, or even impossible. A particularly illustrative example would be sensors being built directly into structure. One could imagine, for instance, embedding such systems in concrete to monitor the condition of hydroelectric power plants or other large technical facilities over long periods of time. For now, however, the diamond battery is one thing above all of these, an exciting technology of the future. It is a technology that could hold great potential for very specific niche applications, but is very unlikely to hit the market in the foreseeable future. It will likely take many years or even decades of costly research before that happens. And now I'm curious, what is your opinion on this topic? Please write it in the comments. I'm always so happy to read all these beautiful comments, also all the nice things you say. Thank you so much. Vielen Dank, we say in Germany. And I say auf Wiedersehen, which means goodbye. See you next time, your Jacob.